Good morning, students. Myself, Dr. Eustace Russell, working as Assistant Professor, the Department of Mechatronics Engineering at Sri Muthukumaran Institute of Technology. So far, we are seeing the subject called Kinematics and Dynamics of Machinery, subject code of MR3451, coming under the regulation of 2021 for the semester of 4th semester for the second year students. So, for the previous videos, you have seen the Unit 5, the introduction part of balancing we have completed, and followed by the second video lecture we have seen some basic problems in balancing of rotating masses we have completed, and today we are going to see the second half of the Unit 5 called vibrations, a very interesting subject. This is the second half of the Unit 5. One problem they will ask from the balancing of rotating masses, and the second half they will ask the problem from the vibrations, free vibrations. So you will see one by one. So these are the syllabus coming for vibrations. That is free vibration, first one. The second is equations of motion, followed by natural frequency. Then the problem we will focus on the bending critical speed of simple shaft. We will see one by one. So before go on to the topics, we must know the basic definitions of free vibration. We will see one by one. That is basic features of vibratory systems. First is periodic motion. The motion which repeats after a regular interval of time is called periodic motion. The motion which repeats after a regular interval of time is called periodic motion. Then frequency. Number of cycles completed in a unit time is called frequency. So what are the number of cycles that is complete in a particular unit time, then it will be called as frequency. Its unit is cycles per second, that is CPS or hertz. Time period, time taken to complete one cycle is called periodic time. It is represented in seconds per cycle. Then amplitude, maximum displacement of a vibrating system or a body from the mean equilibrium position is called amplitude. Then free vibration. When the system is disturbed, it starts vibrating and keeps on vibrating thereafter without the action of external force. Such vibration is called free vibration. This everybody knows that when a system is disturbed, it starts vibrating and keeps on vibration without any action of external force. Let us take a string or anything, a rod or anything. On concrete rod with is left out after the incomplete of the construction. If you are striking a rod with some any equipment or any device for a period of some cycle of time, what will happen to the rod? It will get vibrate for a particular time seconds. That is called as free vibration. The natural frequency is nothing but when a system executes free vibration which are undamped. The frequency of such a system is called natural frequency. That is called a damped and undamped is there. So based on that, it is called natural frequency. Then forced vibration. Forced vibration is nothing but vibration of the system under the influence of an external force are called forced vibration. So based on some external force, you are applying some external force, then some vibration will happen. The frequency of the forced vibration is equal to the forcing frequency. These are the various features. Everybody must know that, the basic definition of that. A very important thing, periodic motion, frequency, time period, amplitude, free vibration, natural frequency, and forced vibrations. Then degrees of freedom, that will be in short form, we will call as DOF. DOF, degrees of freedom. Number of independent coordinates required to completely define the motion of a system is known as degree of freedom of the system. The first unit itself we have discussed mainly about the degrees of freedom in the first unit. That is especially in the inversion system, inversions of various mechanisms, we have seen these degrees of freedom also. Links, joints, and various pairs also we have seen this. Then free vibration of longitude, transverse, and torsional systems of single degree of freedom. First is called longitudinal vibration, and second is called transverse vibration and torsional vibration. Longitudinal is nothing but the rod or anything, the object that is vibrating along a vertical manner. We can see that it is a longitudinal vibration. Transverse means just like a pendulum one. It is moving to the right or left. It is acting in a that is followed by SHM. Like that, it is moving in a pendulum manner. That is called transverse vibration. Then the next one is called torsional vibration. Torsion means some twisting movement will be given to the that is rod or any shaft. So automatically that torsion vibration will be recorded in the last case, the last diagram. Then equilibrium method or Newton's method. That is the equations of equilibrium. We have the constraint that we are taking as a spring of negligible mass is unstrained. S is the stiffness of the constraint. It is the force required to produce unit displacement, the direction of vibration. It is usually expressed in Newton per meter. M is the mass of the body suspended from the constraint in kilogram. W is the weight of the body in newtons, that is mg. Del is the static deflection of the spring in meters due to weight W, that is newtons. X is the displacement given to the body by the external force in meters. So first figure is constrained position, and second is the after displacement what will happen, some the change in displacement will happen, that is a del will be noticed here. Then the stiffness of the constraint is also given here, that is del plus x. It is actually long derivation will be there. Derivation is not at all very important, but you must know the formulas. That is very much important. That is Fn equal to 1 by 2 pi. Everywhere we are using this formula, root of 9.81 by del, which is equal to 0.4985 by root of del x. This formula is very important for solving the problems. Then by energy method, we have the expression like this: d square x by dt square plus s by m into x is equal to 0. Then basic problem in vibration. This must I already told in the previous one. Basic problem, basic formula we have noticed here, there, and we are using the formula here. The car having a mass of 100 kg deflects its spring 4 cm under its load. Determine the natural frequency of the car in the vertical direction. So it is given mass is equal to 1000 kg, del equal to, that is a deflection, spring having a deflection of 4 cm, converted into meter, that is 0.04 meter. The natural frequency of n equal to 1 by 2 pi root of g by del. Therefore 1 by 2 pi root of 9.81 by 0.04, you will get 2.492 hertz. The damping force per unit velocity is known as damping coefficient. The whirling of shaft and critical speed. Speed at which resonance occurs is called critical speed of the shaft. In other ways, the speed at which the shaft runs so that the additional deflection of the shaft from axis of rotation became infinite is called as critical speed. Critical speed occurs when the speed of the rotation of the shaft is equal to the natural frequency of the lateral vibration of the shaft. At this speed, shaft starts to vibrate. The transverse direction whirling is defined as the rotation of the plane created by the bent shaft and the line of center of bearings. This whirling speed is nothing but due to the bend of the shaft. That is also, it is mainly example we can notice here. Rotor blades of the turbine may come in contact with stator blades. Rotor blade, because of that, that is a whirling speed. Because of that whirling, this will happen. Larger shaft deflection produces larger bearing reactions, which may lead to bearing failure. Amplitude built up is a time dependent phenomenon, and therefore it is very dangerous to continue to run the shaft at its critical speed. It is a very danger one, and you have to reduce that one also. This mainly essentially depends upon the eccentricity of the center of gravity of the rotating masses from the axis of rotation of the shaft, diameter of the disc, span or length of the shaft, type of support, connections at its ends. Then critical speed, the continuation of that one, we have two expression. We will notice that we can see here. In a shaft whirling situation, y is the additional displacement of CG from axis of rotation. CG is nothing but center of gravity due to the centrifugal force. Y varies with respect to operating speed and critical speed. Then y equal to plus or minus E by nc by n whole square minus 1. If the operating speed is equal to the critical speed, then it will be the denominator part will become 0. Therefore, y equal to 0. Then there will not be any deflection. Then nc will be 0.4985 by root of del RPS. Again, the expression will goes on like this. Critical speed of the shaft is same as the natural frequency of transverse vibration. How to justify this means omega c equal to omega n equal to root of s by m, which is equal to g by del root heads. If nc is the critical speed in RPS, then 2 pi nc equal to root of g by del. Then nc is nothing but 1 by 2 pi g by del root. Then that is equal to 0.4985 by root of del RPS. Hence it is proved. These two are equal. This is the reference which I used for preparing this content. Kindly go through these references. Thank you students for your kind attention. So today we have seen the vibration basic concepts. All of you go through it. Kindly subscribe the channel, share this video to your friends. So we will see in the upcoming slide of this unit 5. Thank you students.